Well friends, having introduced the transfer function of a plant, that is modeling of a plant and models of disturbances and the test signals, probably today onwards we can take up the dynamic response of the system. So, I will like to take the block like this. This is the plant. This is modeled by the transfer function Gs. To this plant we have the input Rs and the output is given by Ys, and I know the general nature of Gs and the type of inputs we are going to handle. Recall, the step, ramp, parabolic inputs are the models of the disturbances as well as they are the models of test signals for the purpose of analysis and design. So, as such the output becomes Ys equal to GSRS, that is in the Laplace domain the convolution is transformed to an algebraic relationship. Now, the dynamic response, that is the output Yt, if I am interested in, I will get first the value of Gs, then the value of Rs, therefrom the value of Ys, inversion of Ys will give me the value of Yt. Since the Laplace transform and its inverse, this is tabulated in various textbooks, we will not go to the details how these tables or how this inversion formulae are obtained. We will rather use these tables for the purpose of inversion, and I think it will be appropriate if I quickly give you couple of examples, though nothing new in this particular case, but still, as I said, in having an overall setting of the control systems analysis and design, these quick review examples will be helpful. The example I take is the following: Gs, the plant model, is equal to 1 over s squared plus 3s plus 2. You can just say numerator polynomial is 1 and denominator polynomial is a second order. Numerator polynomial is a 0 order polynomial, let me put it this way, and the denominator polynomial is a second order polynomial. The system under consideration is a second order system because the highest power of s determines the order of the system. Let me put it in the pole 0 form. There is no 0 in this particular case, and there are two poles at s is equal to -1 and s is equal to -2. These are the two poles of this particular system. How about the input? Consider an input RT equal to phi mu t, a step input of magnitude phi. Therefore, as you know, in this particular case Rs will become phi over s. Okay? So, the algebraic relationship Ys is equal to GSRS gives me the response transform as 5 over s into s plus 1 into s plus 2. Some of the terms which I will be defining you should please note, because these will be referred to again and again later on. So, in this particular case there are three poles now as far as the response transform is concerned: the pole at s is equal to 0, the pole at s is equal to -1 and the pole at s is equal to -2. If I am interested in Yt, so naturally the partial fraction expansion and inversion of Ys will give me the value of Yt. So, help me please, what is the partial fraction expansion for this? At s is equal to 0, I get the residue as 5 by 2. So, one term is 5 by 2 by s. At s is equal to -1, what is the residue please? It is -5. So, the other term becomes -5 over s plus 1. At s is equal to -2, it will become plus 5 by 2, I hope. So, it is plus 5 by 2 over s plus 2. Please see if there is any error here. The point I want you to keep in mind is the following: these are the terms because of the system poles, please. You recall the transfer function had the poles at s is equal to minus 1 and at s is equal to minus 2. This is the term which is because of the excitation pole. The step input gives rise to this particular pole. Now, if I invert this y s, I get y t, very simple. This is equal to phi by 2 t minus 5 e to the power of minus t plus phi by 2 e to the power of minus 2 t. Now, just see, let us just classify the terms over here. What are these terms? These terms are contributed by the system poles when excited by the step input. Please see, the poles are excited by the step input and they result in the response is given by these two terms, and as you see that these two terms die away with time. As t tends to 0, these terms die out, and I refer to these terms as the transient response of the system. Yes, please, any question? Oh, I am sorry, it is phi by 2, it is the inverse of phi by 2 by s. So, it is phi by 2. Now, look at this term, this is a contribution due to the excitation pole, and you will please note that the nature of this contribution phi by 2 is same as the nature of the input itself. The only thing is that the magnitude has got modified, and this modification in the magnitude is dependent on the reaction of the system to the input. Since the input persists for all time, this particular response will persist for all time and is referred to as the steady state response. Okay. Now, the steady state response, as you know, you can also get without resorting to getting the total time response of the system. You can apply the final value theorem to obtain the steady state response. Okay. Let me put this theorem also for your benefit, revise the theorem for you. Limit t tends to infinity y t. I am interested in the final value of the variable y t. This is equal to, as you know, limit s tends to 0 s y s, where y s is the transform of y t. Provided, this point may please be noted, provided s y s has no poles, on j omega axis right half plane. This point, the applicability of the final value theorem may please be noted. Many a times we make an error here. So, this final value theorem will give you the correct result by using this particular relationship, provided s y s has no poles on the j omega axis and are in the right half plane. So, if I apply this theorem, you recall in this particular example under consideration, the steady state value is phi by 2. So, if I apply the final value theorem, s y s, as you know, is equal to 5 s over s into s plus 1 into s plus 2, and therefore, y double s naturally by the final value theorem turns out to be phi by 2. So, it means if we are interested in the steady state behavior of the system, in that particular case directly this theorem can provide us with the results. In this, for this particular numerical example under consideration, the response looks like this. This is your t, this is y, this was the input, the value is phi, and the output is an exponential rise to a value which is different than phi. This is the exponential rise, as you see, and this particular value, the final value, the steady state value is phi by 2. Okay. Nothing new in this example, I know, but still some of the terms which we are using over here, they will be used later on, and hence acquaintance with these terms will be quite useful. Another example, one more example if you can bear with me. The other example I will like to take is the same plant Gs over S plus 1 into S plus 2, that is the two system poles at -1 and -2. But now I take the input as R t equal to 5 t mu t. Okay. It is a ramp input as you see. So, for this ramp input 5 t mu t, the transform domain expression is, as you know, phi by s squared, and therefore, the response transform y s now becomes equal to 5 over s squared s plus 1 s plus 2. Okay? This is the response transform. Now, I want to invert this, the same procedure. Now, let me retain this here, and I want to get the partial fraction expansion for this. This y s is equal to, I need your help please, what is the term corresponding to s square, what is the residue? As you know, in this particular case the residue will be, substitute s is equal to 0, it is going to be 5 by 2. The other terms are going to be plus, let me take some constant k over s. This k I am going to determine, but let me proceed further. The next I take is at s plus 1. So, let me substitute s is equal to -1, s is equal to -1 gives me 1 here, the s is equal to -1 gives me 1. So, it is going to be plus 5 over s plus 1, and the last term please, s is equal to -2, 4 and a minus sign here. So, it is minus 5 by 4 over s plus 2. Okay? Now, look at this residue k. I hope you will recall this. What is k? K will be equal to d by ds of 5 over s plus 1 into s plus 2 at s equal to 0. This is because of the repeated pole. The pole at s is equal to 0 is repeated, the multiplicity is 2, and therefore, it will give rise to two terms in the partial fraction expansion. One, s square term coming in the denominator, other s term coming in the denominator, and s squared is directly given by putting s is equal to 0 in the term remainder term when s squared is removed, while s is given by this expression. Now, look at the value of k. In this case now, k equal to d by ds of 5 divided by s squared plus 3 s plus 2 at s is equal to 0. This is equal to, yes please, minus, take the derivative of this, 5 over s squared plus 3 s plus 2 squared over here. What else? The term here will be 2 s plus 3. I hope this is okay. Please do help me if there is an error. Now, if I substitute s is equal to 0 here, I get this as equal to minus 15 by 4. Okay, minus 15 by 4. So, this term now is replaced by minus 15 by 4, and therefore, I can rewrite the total expression y s equal to 5 by 2 s squared minus 15 by 4 by s plus 5 by s plus 1 minus 5 by 4 divided by s plus 2. This becomes the partial fraction expansion for this case when the system is excited by a ramp input. Now, let us see the behavior of the plant when the plant has been excited by a ramp input, and the behavior will come out easily when I take the inverse transform of this. Inverse transform will be given by 5 by 2 t minus 15 by 4 plus 5 e to the power of minus t minus 5 by 4 e to the power of minus 2 t. Look at these expressions now. You will find that these are the terms which have been contributed by the system poles, and these terms reduce to 0 as t tends to infinity. This is the transient component of the total response. Look at the other component. This component is due to the reaction of the system to the input in this particular case being ramp. So, this is also of the similar nature as you see, and therefore, I can write over here y steady state. The steady state is equal to 5 by 2 t minus 15 by 4. This is the steady state response of the system. Look at the nature of the response. It looks like this. This is your value 5 t, that is the ramp input, and the response will be something of this nature. So, I can put it this way, that this is 5 t and this is 5 by 2 t minus 15 by 4. I told you to be a little cautious when applying the final value theorem. Look at this particular case. What is YSS? If I apply the final value theorem to this, limit s tends to 0 SYS equal to limit s tends to 0, it is s over s 5s over s squared s plus 1 into s plus 2.
Is it correct, sir?
This has to be.
It will start from negative.
I am sorry. You are very right. Actually, I have to plot the total transient. This graph is right. I like to rectify this, please. You are very right. Yt is equal to 5 by 2 t minus 15 by 4. Yes, let me look at the total response, please. Plus 5 e to the power of minus t minus 5 by 4 e to the power of minus 2 t. Please see, this is the graph when t is equal to 0, your what is the value? The value in this particular case at t is equal to 0, please help me, will turn out to be 0. Check this. So, it means the graph which I have plotted is the graph of this yt. Okay. YSS component is equal to minus 15 by 4 plus 5 by 2 t, please. This is your YSS component, the steady state component as t tends to infinity. The graph I plotted is that of the total response yt, which is equal to this particular expression. This can be checked, please. Now, I was referring to the final value theorem. So, coming to this expression, please see, your steady state is given by this. Coming to this expression, if I apply the final value theorem, YSS is equal to this. Now, please see, if you do not take care of the condition on the poles of SYS, the final value turns out to be infinity. But however, what is SYS? SYS has a pole at the origin, and therefore, in this particular case final value theorem is not applicable. You have to be very careful about this. The final value theorem gives the result as infinity, while the basic time response analysis shows you that the steady state response of the system is given by this expression minus 15 by 4 plus 5 by 2 t. The steady state on the time axis starts as soon as the transients die out. Okay. So, this is the expression, and this expression naturally as t tends to infinity goes to infinity. So, the two values will match at t tends to infinity, but the total steady state expression is not given out by the final value theorem in this particular case, because SYS has a pole at the origin. Okay. Right. Now, after giving you the dynamic response review, I mean more examples need not be given. taking the Laplace transform of input and the plant, inverting that to get the response was nothing new to you, but I hope the review of the dynamic response analysis which has been given will be useful. And I am going to use this particular dynamic response analysis review in setting up or in giving you the characteristics of first order and second order models. You may say that why out of nth order models where n can vary from 0 value to any number, first and second order models have been taken out for a specific study. The reason being, the systems we are going to come across, you will find can appropriately be modeled in terms of first order and second order terms. They play a very important role in the modeling and in the design exercise of control systems, and your specific attention is needed to certain parameters which define the basic characteristics of first order and second order models. Okay? I take first a simple first order system. Well, an inertial load with moment of inertia j. This I take as a rigid shaft. By rigid shaft I mean to say is that the spring constant for this particular shaft is 0. It is not flexible, and the friction environment of the system, let me schematically represent it like this. The friction environment and the viscous friction coefficient I take as B. Let me say the attribute of interest to me is omega, the speed, and the input is the torque T applied to this particular shaft. This is the system environment, and as you will see, this can be appropriately modeled by a first order transfer function model. Okay? I hope the situation is very clear. The two parameters of the system are J and B. The input variable is T, the torque applied, and the output variable of interest to me is omega, the speed, omega t, tt, these are the functions of time. J and B are constant parameters of the system. I hope you do not need any explanation to this particular equation. I can write the equation as j omega dot j into acceleration plus b omega b into velocity is equal to T, the torque applied. This is the basic differential equation model for this particular system. The Laplace transformation gives me J s omega s plus b omega s equal to T s. You will note, without specifically mentioning it again and again, the system under consideration will be considered as a relaxed system. That is why the initial conditions do not appear in this transformed equation. The transfer function model of this system becomes G s is equal to the output omega s divided by the input T s equal to s 1 over J s plus b, which obviously is a first order model. Let me repeat this expression, G s equal to omega s over T s equal to 1 over J s plus b. Now, in this particular case, the parameters of the system are J and B. The characteristics of a first order system, any first order system, be it mechanical, thermal, electrical, liquid level system or any other system, you see they come out in this particular form very nicely. that is a general model I am going to take as k over tau s plus 1. This is also a first order expression, but written in a different way, where the parameters now are k and tau. The k is referred to as, it will become clear as to why this name is given. This k is referred to as the system gain, and the tau parameter is the time constant of the system. Time constant of the system. Now, see this particular situation. The input T s is equal to 1 by s. I give a unit step input to this system under consideration. In that particular case, the response omega s is equal to k over s into tau s plus 1, and the inversion of this gives me omega t equal to, I think now I can directly write, this could easily be verified that this is going to be the expression as far as the time response is concerned. Look at the system gain please. K is a parameter. As t tends to infinity, the speed omega becomes k. So, it means the speed of the system changes to a value k in response to a unit input, unit step input, and that is why the name system gain is appropriate for this particular parameter k in the general first order model. It changes the output of the system by k. This is the reason, probably is the most appropriate reason to say that why the word system gain is used for this particular parameter. Now, let us look at the time tau, that is the time constant tau. For that, I will like to make a sketch of this particular response. If I make a sketch of this response, this is omega and not y please, t versus omega. In that particular case, you see that the final value is k given over here, and this is the transient component minus k e to the power of minus t by tau, which goes to 0 as t tends to infinity, and the total response is given by this green curve k 1 minus e to the power of minus t by tau. Now, look at the decay of this transient term. Look at the decay please. This particular transient term minus k e to the power of minus t by tau, if I take the derivative of this at t is equal to 0, you can easily ascertain, please see that this is k by tau. So, it means this is the slope of this particular transient term at t is equal to 0, initial slope. So, it means this particular term starts decaying with an initial slope of k by tau. If the slope would have been constant, if the decay slope at t is equal to 0 would have continued, this particular term would have come to 0 at time t is equal to tau and is referred to as the time constant of the system. This is a very important parameter, as I am going to explain to you. The time constant of the system represents the time for the transient to decay if the decay were dictated by the initial slope k by tau. Now, look at the actual value. Now, the slope is not constant, it is changing. Look at the actual value. At t is equal to tau, the actual value is 0.3679. In that particular case, I can say that the actual value at this particular point is minus 0.3679 k. This is the actual value. Similarly, if I proceed and calculate at 4 tau, it is 0.0183. At 5 tau, it is 0.0067. So, you can say that in this particular situation, in a time roughly between 4 to 5 tau, where tau is a characteristic parameter of the system, the transient of the system has almost decayed to 0, because you see mathematically if you see the decay will come as t tends to infinity, but we have to take up the practical value. The practical value in this particular case 0.0067 can be taken as approximately equal to 0, and therefore, in a time roughly equal to 4 to 5 time constants, the transient of the system has decayed, or equivalently I can make a statement, the system has settled down to the final steady state. After all, this is the total time response, this is the total curve of the system. The system has settled down to the steady state in 4 to 5 time constants. So, what is the time constant parameter? Can I say that in terms of control system terminology, the speed of response is a very important characteristic of the system, speed of response. When an input comes on a plant, we will like that the plant immediately responds. Theoretically speaking, I want the plant to respond instantaneously, but it is not possible, the instantaneous response is not possible because of the lag components in the plant. Now, you see that this particular response should be as fast as possible. Now, if I interpret this in terms of time constant of the system, since the response decays in 4 to 5 tau, so it means the faster response will be obtained when the time constant of the system is low. So, it means larger the time constant of the system, I can say sluggish is the response. These terms I will be using quite often, because these first order factors will be appearing quite often in our exercise on analysis and design. So, what is a sluggish system? A sluggish system will have a larger time constant. The process models, let me make a mention over here. The process models, by process I have defined these terms: control of temperature, liquid level, pressure and the like, the chemical composition. These are the process control applications. These are typically characterized by large time constants, that is, these are sluggish systems. Take for example, the examples we have taken of speed control or radar tracking system. These are characterized by smaller time constants and hence are fast systems. Please see that the time constant of a typical system may vary from milliseconds to a few minutes. The example of milliseconds being that of the speed control system or a tracking system, the radar tracking system, servo mechanism for steering of an antenna, and that of a minutes could be the temperature control and the like. So, you see that this is an important characteristic parameter of the system, the time constant, and 4 to 5 time constants gives you the total time for the system to settle down to the steady state environment. Okay. One more definition I like to give over here, which I will be using, the terms of the type k over tau s plus 1. I will be using the terms for this first order lag. Now, the word lag becomes clear. Why the word lag is coming? Because it is not allowing the system to respond instantaneously. This is a first order lag, or sometimes in the control system jargon, simple lag is also used for terms of the form k over tau s plus 1. So, can I use the word this first order lag or a simple lag is completely characterized by these two parameters k and tau, and therefore, the personality of a first order system is completely characterized by the two parameters k and tau, k being the system gain and tau being the time constant of the system. Okay. Similarly, I will like to take up a second order system and find out the minimum information which describes or which characterizes the total personality of a second order system. For you to focus attention on the discussion on second order system, I like to make a mention that all the higher order systems, maybe 4th order, 5th order or even 10th order, as you will see later in our total design exercise, are appropriately approximated by a second order system. I need your attention on second order system because the second order system is going to play crucial role in our total design exercise. What we are going to do later, I am going to convince you, not that just we are going to take a second order system as the approximation for any higher order system. I am going to convince you that in most of the situations we come across in practical situations, in practical systems, the higher order systems of any order, even up to 10th order, can be appropriately approximated by a second order, and hence our design can be carried out using a second order approximation. And therefore, we should concentrate on the parameters which describe the personality of a second order system. Okay? And I like to give an example of a second order system as well, and the example I give you is that again of a load with moment of inertia j, but in this particular case I make the shaft flexible. In this particular case the shaft is flexible, the torque T is the input, let me make it a function of time, and let me write it here specifically that it is a flexible shaft, and let me take the spring constant for this, the parameters which describes this attribute of the shaft is K. As I did earlier, the frictional environment is schematically represented like this, and let me say that B is the viscous friction parameter. And in this example now I take the position theta as the attribute I am interested in. Theta, that is the position, the twist of this particular shaft is the attribute I am interested in. So, this becomes my output variable. So, input variable here, output variable, and the system parameters which are the constant parameters are j, b and k. You will note a change here please. I have specifically taken a small k here and not a capital K, because I have reserved capital K for the system gain parameter. So, this point may please be noted in your notes as well. This is a small k I have taken to distinguish it from capital K, which I have reserved for use as a system parameter, as a system gain parameter in the general transfer function model. So, let me write the differential equation model for this particular expression. Help me if this is okay. J theta double dot is your acceleration, plus b theta dot velocity here, plus k theta the displacement is equal to T the input. This becomes your differential equation model for this particular system. This is a second order differential equation. So, it is a second order system. In the transfer function form, as you will see, a second order characteristic polynomial will appear. Gs, the transfer function of the system, is now given by the output variable theta s divided by the input variable Ts is equal to 1 over Js squared plus Bs plus k. This becomes the transfer function model of this system. The output variable is displacement and the input variable is t, and this of course as you see is a second order model with j, b and k as the 3 parameters of the system. Again j, b and k are the specific parameters of the system under consideration. I am interested in general parameters, so that those parameters have physical meaning and they become applicable to any system we come across. And the general parameters, you already have the information about those parameters. As I said, it is a review sort of thing. To put it in the control system setting, the general parameters as you know are omega n, the natural frequency, zeta, the damping ratio and k, the system gain. So, it means this particular expression can be written in this form now. and this is a second order standard model with these as the parameters. Specifically, in terms of the parameters of the system under consideration, the values of k, the system gain, the value of omega n, the undamped natural frequency, the value of zeta, the damping ratio can easily be obtained as given over here. You can easily check this. Okay? These are the three parameters. Now, I want to look at the physical meaning in terms of a control system. What is the physical meaning of the terms k, omega n and zeta? And to get the physical meaning, I will proceed the same way. That is, this second order model will be excited by a step input. I will study the response of this particular system to a step input, and I will see how the system behaves or how the response behaves for different values of k, omega n and zeta. The k has the same meaning. This you can check by the final value theorem as well. You see that for a step input, please help me, you can immediately check. For a unit step input, the final value of the response is given by k. Just immediately apply the final value theorem and check, please. So, it means this is the gain of the system. Okay. So, now I have to concentrate on the parameters zeta and omega n, because my claim is this, that k, zeta and omega n, these three parameters describe the personality of a second order system in general.
So, but is the theorem always applicable?
Your question, please, can you speak it again?
Is the final value theorem always applicable to this form?
No. That was for you to examine. I thought you have examined it straight away, whether it is applicable or not. Let us say, so in this particular case, ys for a unit step input is 1 over or k into, this is k over s into 1 over omega n squared s squared plus 2 zeta omega n s plus 1. It is for you to test. I have given you the general condition of applicability. Sys becomes equal to, as you see in this case, k over 1 by omega n squared s squared plus 2 zeta by omega n s plus 1. So, in this particular case, as you see, as s tends to 0, the poles of this should be there in the right half plane. This is the only condition of getting the value of k as the final value or steady state value. So, if I assume that the values of omega n and zeta are such that the roots of this equation are in the left half of the s plane, the final value theorem is applicable, and limit s tends to 0, Sys becomes equal to k, that the system gain of the system under consideration. Okay. So, as I said that to study the parameters zeta and omega n, I like to take the response of the system, and the response, now having given you couple of examples, really I will not like to take the complete response of the system and have too much of repetition. Since you already know, I like to put it in the final expressions only. Theta s over T s is equal to k omega n squared over s squared plus 2 zeta omega n s plus omega n squared is the expression. Remove T s from here and have the s value here. This becomes your transform, response transform theta s. What you have to do is, you have to take theta t is equal to Laplace inverse of this theta s. I will be writing the expressions directly. I have taken it in my notes, but you can definitely, for different values of omega n and zeta, you can take the inverse Laplace transform and verify the expressions of theta t, which I am going to write. I will take up 4 cases. Case 1 will correspond to zeta equal to 0. You see that zeta equal to 0 is a case corresponding to b is equal to 0. That is no damping, underdamped case. The second case I will take zeta is greater than 0, less than 1. The third case I am going to take zeta is equal to 1, and the fourth case will be zeta greater than 1, and all these cases correspond to damped case, that is B is not equal to 0. These are the 4 cases I will take, and we will see as to how the response behaves and how it characterizes the behavior of a control system or a system under consideration. Case 1 I am taking, and I have given you the expression for theta t directly here, which can be obtained by inverting theta s corresponding to the response transform given to you earlier. So, zeta is equal to 1 is the case, and theta t is equal to k 1 minus e cos omega n t, and as you see it is an oscillatory response oscillating around the value k. Since these are oscillations when damping is equal to 0, you can say that these are undamped oscillations, and the name omega n is given as the undamped natural frequency, because this is the oscillating frequency when damping B is equal to 0 or zeta equal to 0. So, this is the behavior of the system, an oscillatory behavior when the damping is 0, and naturally in a control system normally you will not like to go for this behavior. When you take up all the 4 cases, please keep in mind you should relate to the acceptable behavior in an industrial environment. That is how the system, a control system, should behave. Naturally, in most of the cases this type of oscillating behavior will not be acceptable. Can you recall an example in which I made a mention that this type of oscillating behavior may be acceptable? If you recall, that is the example of residential heating. With the on off control system, in that residential heating system, you see the output of the system was oscillating output, oscillating within certain temperature band. So, the acceptance of this oscillating behavior is dependent on your requirement of the system, but in most of the situations, industrial situations, such a behavior is not acceptable. Okay? Let me now take up the underdamped case, of zeta greater than 0 less than 1. So, this case corresponds to this restriction on the system parameters where can easily be verified, and this is the corresponding response, this also you can easily obtain. Now, in this omega d is the term used over here, and this omega d in terms of omega n and zeta is given by this expression. This omega d is referred to as damped natural frequency. The name will become, the reason for this name will become obvious when you look at the response curves. The damped natural frequency is omega d. Look at the response curves, the green curves in this expression please. The green curves correspond to zeta greater than 0 less than 1. As you find over here that this particular expression now is again an oscillating behavior, but the oscillations are damped. The oscillations in this particular case are damped, please say. If you increase the value of zeta, let me take a typical value of zeta over here. Typical value of zeta is equal to 0.3, let us say. So, if you increase the value of zeta equal to, let us say, 0.6, what will happen? You find that the change in the damped oscillations and the change in the peak overshoot which is appearing over here. If you further increase the value of zeta, you get this particular curve, which is the curve corresponding to zeta equal to 1. So, zeta is equal to 1 corresponds to the limiting situation where the oscillations have just died out. It is a limiting situation. So, what will happen? Just for a value zeta a little less than 1, for a value zeta a little less than 1, there will be oscillation. Okay. So, this is a limiting case. On the other hand, the limiting case is given by zeta is equal to 0, where the oscillations are undamped. So, you find that the green curves correspond to the situation zeta greater than 0 less than 1, the so called underdamped case. Underdamped I will like to put, underdamped case. And most of the situations in control systems belong to this particular subclass. That is, this is the requirement normally you impose on the control system. You can see at this juncture as to why you impose this requirement on the control system. You will find that as your green curve approaches this blue curve, and or further if you increase the value of zeta, the settling time or the speed of response of the system becomes poor. That is, the system becomes sluggish as the value of zeta increases. But if the value of zeta decreases, that is, if you take the value of zeta close to 0, what will happen? The system becomes too oscillatory. So, you please see that the situation, the sandwich situation between zeta is equal to 0 and zeta is equal to 1, taking the response closer to zeta is equal to 0 gives you an oscillatory response, too much oscillatory, which may not be acceptable to you. Taking zeta towards 1 gives you a sluggish response, which again may not be acceptable to you. So, in most of the practical situations, you impose a requirement on the system, the zeta requirement, to be between 0 and 1. Well, specific situations could be zeta is equal to 1 as well. Take for example, a robot control system please. If a robot has picked up certain payload and it has to place the payload at some other location, probably you will not like that the system should oscillate. Take for example, the Maruti car example, a robot really does the welding there. It is doing the welding. Now, you will not like the welding torch to oscillate. So, it means in that particular case, for that particular situation, even at the cost of speed of response, you may like to go for zeta is equal to 1, because the oscillations cannot be tolerated in this type of situation. So, you see, for specific situations larger value of zeta could also be accepted, but normally it is between zeta greater than 0 less than 1, that is mostly your industrial controlled systems are underdamped systems. Now, look at this place, this is a typical underdamped response I have taken over here, and this is the envelope of this particular response. The blue curve is the envelope of this response. So, you see that this can easily be ascertained, this can easily be examined. These are the two envelope expressions. So, it means the decay of this response depends upon the decay of the envelope, and this particular envelope decay is guided by this particular exponential factor. The time constant of this factor, can you tell me please, what is the time constant of this factor? The time constant is given by the expressions of the type e to the power of minus t by tau. So, you find that tau is equal to 1 over zeta omega n. So, the time constant of the envelope is 1 over zeta omega n, and therefore, the decay of the envelope is guided by this particular product zeta into omega n. The larger the value of the product zeta into omega n, smaller is the value of the time constant, and hence faster is the response. Okay. So, one more slide I will quickly like to give you over here. The third case is zeta is equal to 1. So, this corresponds to this k by j expression, this is the theta t expression. As you find that the underdamped, this is a critically damped case, critically damped, and in this particular case your response is just oscillatory, just the oscillations have been killed, you see. Over damped case is not accepted. So, it means our control systems performance specifications mostly demand the underdamped case zeta greater than less than 1 greater than 0. On the borderline situations, zeta equal to 0 or zeta equal to 1 may be accepted. Thank you very much.